Today, I want to talk about a little bit of research that I used to do when I was in school, sort of like financial applications of graph network theory, just to get some, a little bit change of topic, give you more application side of where it can be used in finance. This is going to be some quick agenda. So today I'm going to talk about index tracking and some basics of graph. I'm sure everyone's really familiar with what graph is for past 4 days of introductions. So I'll go really briefly about the graph theory and some theories in finance and some applications of what I solved in index tracking. So what is an index tracking? Index tracking is sort of like you're selecting some smaller subset of assets to build some sort of ETFs or within a larger index to track the index, replicating the performance. So what is the advantage of those compared to other investment style like active investing? Well, all the pools are sort of like limited and selected for you. So it's a very like either large cap stocks, mid cap stocks, or you have very well diverse set of like companies. And you're dealing with like smaller subset of assets rather than like the whole market, try to cherry pick like what will be the performing the best. And because of that, like you don't have high active management fees and whatnot. So the big, I guess to everyone's surprise, like the passive investment is just as big as an active investment, just roughly about $15 trillion for estimated asset under management. So, everyone should make money. So what is the true benefit of this index tracking? Well, diversification. So like you're really exposed to broad markets. Like you can be in like typically S&P 500. Most of them are in tech, but you have some exposure to like medicals or some minings, some technology, some semiconductors, etc. It's also very cost efficient. You don't have to have a large set of like analysts to look for what companies to pick. You don't have a big portfolio managers managing a lot of money. And it's really transparent. So things like what you're buying, what companies there are, and you can sort of like predict what the performance is going to be based on the selective companies. And it's really simple. It's really easy to understand. It's really engaging. Like customers tends to want like what to expect for like what would be the expected return, what could be the drawdowns. It's really accessible, and you can buy all these packages on any brokerage accounts. So key definitions of what the talk is going to be. So portfolio is sort of like a collections of assets, like a set of companies. Return would be some gain or loss of your expected portfolio, so aggregated sum of returns. Risk is a potential for all the investment not going as the way you would expect. So it can be either gaining a lot or losing a lot, depending on what you're trying to do. It can be detrimental if you're gaining too much for passive investing, but there will be like enhanced passive investing, which is sort of like you're trying to beat the index. Active is just maximizing return. But today I'm just going to talk about just strictly passive index tracking. So what's diversification? It's just spreading across your assets. So you're mitigating some of the loss with other companies like higher yields. So it mitigates a little bit of drawdown. So like diversification tends to be good, but over diversifying, not so good. Lots of like big hedge fund managers, they don't like to diversify more than 20 companies at a time. And the way we would measure our performance is tracking error. Just how we're trying to replicate the index, we're trying to replicate the performance of an index. So the performance that we're going to measure is going to be the difference against the index, against the portfolio that we built. All right, so graph theory. What's a graph theory? It's a branch of mathematics that studies some properties, something like relational networks between each elements within the sets. And so the graph consists of nodes and edges, as we are very familiar by now. So nodes and vertices, trigonologies, edges, or edges would be like connections between nodes to indicate the strength of like different nodes. Properties or relational, like biochemistry has their own, like ways of defining protein or element-wise. Finance has its own, physics, dynamical system has its own. So the applications is like really endless. It's growing really fast. I work in finance, and we are also we're really adapting. Like finance tends to be really slow in adapting like new technology and applications, but we're also slowly adapting graph networks within the finance community. So that's also a really good start. So Key concept of index tracking with a graph, so financial application side. So each node represents an asset, a security within the whole network. So it can be a stock, it can be a bond, or if you're dealing with a country, like country bonds, like sovereign bonds, then it can be like company, it can be a different currency for like different indications, trade goods and whatnot. But nodes and edges represent a relationship, like some strength or similarities of each different nodes. Node weights can be assigned. For our talk, we won't be using any node weights, but it can be assigned. So things like market cap or the size of the market or the number of influences, or it can be really like how you want, what you're trying to define, what community you're trying to determine. You'd use different kind of weights. Same with the edge weights. It would represent the strength of each pair of securities or each nodes. And of course, the clustering community is a subset of nodes with strong interconnections of how we define this edge weights. All right. So what is the benefit of index tracking using graph versus a traditional method? Traditional method, we try to estimate the return of a portfolio and try to measure the difference between the index's return and the forecasting. That's really difficult to do, right? But trying to build some sort of like collections of like asset weights, combinations to find those combinations of like which company to pick is very difficult to do, versus using simple correlations or just market graph tends to be a bit more robust. It doesn't change over time too fast, so it's really good. It's more stable. It's also really easy to visualize what you're doing. It also helps you determine things that you would never really have access to, things like sectors or subsectors or industries. You can have more quantitative measure of things. So things like, say, Amazon. It's not just, it used to start as a book selling company, right? But now it's doing like music streaming, it's competing against Spotify. It also does movie streaming, it's competing against Netflix. It also does a lot of like powering different companies using AWS. It also helps power like governments and gets lots of money funding from those. So the revenue of Amazon is so well diverse to the point where its subsectors or industry doesn't really help you diversify those companies. So having some sort of like quantitative way to determine some communities over analysts could be very, very beneficial. So it's more robust and sometimes it builds better portfolios. So some steps of building index tracking portfolios using graph. First, you have to construct the graph. So it really comes down to what you're trying to measure. For us, we're going to use some sort of correlation, just close price, simple Pearson correlation to measure the similarities. And we're going to transform this into a distance, like comparison distance, to make it it's like close to 0 if it's very, very close, similar to each other, and 1 if it's very, very unsimilar. So it becomes a metric space rather than -1 and 1. And we're going to identify the clusters. And within this cluster, we're going to select some assets to build a portfolio. So, graphical visualization. We build a market graph, right? Using the company. We build edges, we build nodes, we assign the weights. And now we have a quantitative measure of each relationship, then we can now start doing some clustering. So we identify clustering based on like either, there's many clustering algorithms that we have talked about. Like there was a Priya who talked about like eigenvalue sorting. There's also, K-means, K-meroids. K-means not so much for index tracking. It's kind of constraints of like what you want to do, but for us, we want to select nodes, and K-means gives you some like 0.5, like mean of something that may not even in the graph, or for our graph metric, like it doesn't quite make sense, but some community detections. Then we're gonna build a portfolio, and hopefully it can make us money. So the data that I used is a public library available to everyone. It's an open library, Operation Research, O'Reilly's library for index tracking. So it consists of 8 different indices from different countries: Germany, UK, Japan, Hong Kong, and 4 from US, large cap, mid cap, Russell 2000, 3000, and S&P 100 and 500. So we will be picking, this will be the distance that we will try to formulate. So we've calculated the Pearson correlation between time series for the past year, and we assign the distance so that distance ranges from 0 to 1. Then we'll make it a bit more robust by using a convex mapping. So it tempers a little bit. A lot of the correlations are very densely clustered to 1, tends to be. So we're going to temper a little just so that it becomes the the gradient, the differential of the different objective for different combination becomes a little bit more prominent. And then we'll build a matrix for the adjacency matrix using this distance. Now, the problem that we'll be having will be multi-objective functions. So one, we want the companies that we select to be the most representative. That'll be sort of like the output of the left side. That just means like selecting K assets that has the maximum, that has a minimum close to all other companies, so like most representative of K assets, and maximizing the diversification. So we're selecting K assets that sort of like maximum, like each combinations of each pairs becomes maximized. So we'll be trying to balance this using parameter of beta and alpha. I can show you how I estimate beta and alpha in the appendix if there's a question, but this is a quadratic binary optimization problem with constraints, which is known to be quite NP hard, right? So we'll be solving this on QUBO with a constraint just for the sake of comparison. And we'll be relaxing this constraint to form it as a Lagrangian relaxations to embed the constraint onto objective. And this becomes a quadratic unconstrained binary optimization problem where quantum computers or quantum inspired optimizations are pretty shown to be superior on optimizing. So what are the constraints we'll be dealing with? For DAX 100, we'll be using 10 securities. For FTSE 10, Hang Seng 10, etc. We have like predetermined like how many assets we want to use to track this index. And this would be the benchmark. How do we calculate the tracking error? Well, it's just the square root of, it's just standard deviation between the difference of the returns against the index and the portfolio that we built. Pretty simple, hopefully. So this is sort of like the performance. Of course, I can show you the runtime later, but like quantum optimizers are really superior in solving like this QUBO type of problems when it becomes like 3,000 nodes network. And the performance is like 1.18% for DAX 100, all the way to S&P 500, the most popular one, like 1.4% tracking error, which is pretty good. So yeah, so using graph to solve some sort of financial application is growing these days, and one applications we're adapting like NP hard problem that it tends to be for the graphs that can be utilized like quantum computers for the future or digital annealers has shown to be quite promising. And yeah, I guess that's like the end of my talk, just to give a brief overview.
Let's thank the speaker for a nice talk. And we have for a few questions. Yes.
This is a softball question. Have you looked at, I'm sure you have you looked at the robustness of your method to correlations that you're measuring? So if I remember correctly, you are looking at 1 year correlation as a measure of similarity. How sensitive it is, your tracking errors to that measurement? For example, if you went to 5-year measure or 20-day measure, how would that change?
So it does change. The shorter we look back, more noisy, but longer look back, somewhat robust because we also account for, but like we also don't have that much data window period. But if the longer we go, it might also not like disjoint partitions of like window period that we were to compare. It also changes a lot. That's due to like one, if you look too short, then you just don't have enough data to stabilize it. But if you have too much data, then what I found is the company business changes. And a lot of markets start to adapt more, so like it's not stationary returns. So either you do other different methods, like either projecting like some of the correlation matrix into like eigenspaces to very smaller dimensions or whatnot. It might tend to be a bit more stationary, but for my experience, like long period and short period is still kind of random.
And that really is still open.
It's an open
work to be done. As you left it off.
I think that was a question. Yeah.
Thank you.
You mentioned that you made some comparisons between Gurobi and the digital annealer. Were the results different? I mean, cardinality constraints are notoriously difficult to solve for, so.
Yeah, so this is sort of like I guess I can go through a few slides. So the black line is running 6-hour Gurobi, like did not add any heuristics. It's just pure basic vanilla Gurobi with constraints and objective function, branch and bound, optimize it. The red line is using digital annealer. So if you look at the objective value itself, not a huge difference, right? But also correlation doesn't tend to be huge difference. So like how much does the objective like global optima or like better optima impacts the portfolio's return or index tracking performance? That's an open-ended research, right? How robust is it? How well is it? That usually comes down to, I guess, back testing. But for pure optimization perspective, a digital annealer tends to outperform Gurobi. Hang Seng is like 80 stocks, so 80 by 80, like 80 node network. So it's pretty small. So Gurobi tends to do pretty good, just as good as QUBO. But as we get larger and larger, sometimes just also this one for just to mention QUBO for digital annealer was running it for 6 minutes. So it's 6 minutes versus 6 hours. But Gurobi tends to get stuck at the local optima, just really not performing that good. So yeah, so it also kind of depends on what you want to do, but for my experience, Gurobi wasn't as good for other purpose-built hardwares.
So basically, he has the off-sample performance.
Oh, sorry?
So online, just as
Oh, yeah.
off-the-sample performance.
Yeah, same graph, and this is like the sort of like benchmark for the portfolio.
One application of this methodology that I want you to confirm could be that you can also look at what's changing the guts of the stock market. So if your clusters are getting, so for example, you have like Magnificent 7 stocks that are dominating the stock market, right? I would imagine that those 7 stocks be a huge cluster, and the job of replicating the index would be a lot easier today than what it was, for example, 10 years ago, just because of the concentration. So do you see a potential for this methodology to actually track the changes in the guts of the stock market, for example?
So when I experimented, depending on the clustering method you use, clusters tends to be, some method would result in more stable clusters. So when I measured like each different like time periods and look at Jacquard similarity, so like how many of the assets within different clusters are in the same like intersection cardinality over union of the cardinality, they tend to be above 0.8 for certain commuting, like some clustering techniques. But some clustering techniques, not so much. It changes over time. So the output of the cluster can vary depending on how you construct the problem and formulate it and solve it. So it really comes down to like what you want to do. It can be more stable. It can be more noisy. It could be almost like random. But yeah, that's what I found.
So this question is related to the gap between the application and the theory. So because of the concept our fund is to diversify portfolio, but in general, this kind of strategy or diversification portfolio in general give us a portfolio less diversity. So very ironical. So how can you reconcile this gap between the theory and the modeling and also the practice in portfolio management?
Oh, I'm glad you asked that question. So that's a great question. So just to repeat that, like how do we bridge the gap between theory and the practical point of view of like how do we ensure like things are diversified and stuff? The truth is we have to just do back testing. There is no other easy way of testing the real world problem other than back stress testing. And back testing is very difficult to do. I'm sure like from your company, you try to do it. It's not as easy because there's so many impacts. Like for the way I interpret stock market is the price is just a reflection. It's a projected like one-dimensional space of how economies are perceived by people, right? So it's really like one-dimensional, but like there's a lot more things that goes underneath the hood of how this price sometimes get influenced. So if you can model like all other aspects of this, like different markets have very strong impact, consumer spending, business spending, relationship, that sometimes is really hard to get by, really hard to do. So And also companies are really like diversifying. If you just look at like Google subsidiary brands, it's exposed to healthcare, it's exposed to mining, it's exposed to tech, it's exposed to like different like goods like phones and stuff. So lots of big cap market companies are not just one single industry, but they're really, really well diverse because they have their own portfolio. Same with like Volkswagen, which is a private company, like automobile company, conglomerates. They are well exposed to other companies. They have different stakes of different companies. So it's really hard to do just one single industry, and sometimes clustering itself may not be good enough, but sometimes it does give insight that you typically would not think of. Like, so it's, yeah, all comes down to like, I guess sometimes you stumble across like a mistake, but that mistake happens to be a pile of gold or yeah, accidents.
The next bigger check, so you're here, okay.
Oh.
So in the interest of time, we'll have to, I think there are some questions on the chat, but just in the interest of keeping the schedule, my apologies to the people in cyberspace.
Oh.